精彩的演讲，特别是关于就是刚刚讲的，就是那个计算机历史的那一段，因为我自己也在做一些就是法律跟计算机相关的事情嘛，然后我也是感觉到，就是很多人只是把这个计算机历史当成了一段程序员的历史，然后是一段计算的历史，但实际上在这个计算机发展的过程中，在软件的发展过程中，实际上有很多人包括这些社会学家、经济学家，包括这些律师，包括一些其他行业的人，实际上都贡献出了自己的就是智慧贡献出了自己的经验的。那我们现在来介绍我们的第二位演讲者，我们的第二位演讲者是这个 Sam Williams。驱动性化存储协议 RWE 的联合创始人和首席执行官。那 Sam 呢，他在分布式系统的设计跟实施方面呢，都具有非常丰富的经验。然后他曾经交付过各种各样的项目，包括这个分布式的操作系统。那他今天演讲的主题是建立一个永远不会忘记的网络。掌声欢迎啊！
Thank you. Can everyone see me and hear me right?
Yeah.
I'm going to say that yes.
Yes, we can.
Okay, great. Perfect. I'll share my screen. Okay.
Perfect.
So thank you. It was a very interesting exploration of some of the history of computing. It's very interesting to hear about the correlation and the differences in the Chinese community and experience of that living in the West. So thank you, that was a very interesting discussion. Okay, so ARWE. It takes a slightly different component of the stack to the prior talk. So ARWE is about building a decentralized permanent store of knowledge and history. I don't want to front. The idea is that we've taken a blockchain, which is a system that creates a ledger which is distributed between many computers, and scale it up so that we can fit very large amounts of information inside. And when we can do that, we can make an archive that doesn't forget information ever, because it is replicated in many different places rather than just in one place. And we see ourselves what would you say? Standing on the shoulders of the giants of the Internet Archive. In fact, we work pretty closely with the Internet Archive for storing metadata about the information that they store inside our ledger, but on top of that, we also store other information. So let's get into it. Okay, first, the motivation for this project. So we were looking, this was about 3.5 years ago now, at the structure of the web itself, and we noticed that essentially what happened somewhere along the path between Web 1 and Web 2 was that you could argue that the web had essentially failed in its initial mission and it had gained another mission which was quite different, and it had pursued that. So the initial mission of the web was to be a globally distributed collection of knowledge that was interlinked. So the hyperlink allowed us to jump from one document to another. That was actually the core innovation of the web. The internet allowed us to do transfer of knowledge at distance, but then the web built on top of this and said, okay, what if that knowledge can then be deeply linked to one another? That was building on ideas that were first put forward in the Gopher protocol, which preceded the web by about 2 or 3 years. Gopher had this same type of for the internet, which is basically just transferring information, essentially instantaneously across very long distances. And you could have documents that were connected to each other. So at the end of each document, there are essentially a bunch of footnotes, and you could click on one of the footnotes, and it would take you to another document. The web, or HTTP, really, just built on top of this and said, okay, what about we make it so that individual bits of text inside each document can link to other documents? That's essentially the innovation of the web. And that's great, and that's kind of the way it remained for a very long period. But it has this fundamental flaw that it is forgetful. So the web doesn't necessarily work exceptionally efficiently at conveying information over long periods of time. In fact, actually, I don't think most people realize just how inefficient it is at doing this. So there are some studies that were published about 4 years ago now that showed that of information that was shared on social media, 35% approximately of that information was lost or fundamentally altered behind links in the first 2 years after publication. And then, staggeringly, 20 years down the line, 98.4% of all data is lost or modified to the point that the initial link doesn't point to the same meme, if you understand the meaning as put forward by Richard Dawkins, essentially like the fundamental version of an idea. So 98.4% of these links break in 20 years, which means that while in society we've come to depend upon the web as our centralized store of knowledge for all of humanity, we're even changing the way we go about the process of learning, such that, because now we know that we can always access information in the world in a sort of abundant fashion. We don't need to store so much information in our heads. Like, the protocol was so strong and so impactful that it has changed the way that we interact with the world on that fundamental level. Yet, it turns out that the protocol itself is extremely forgetful. It has no mechanism for remembering. So the web was built as a kind of library at some level of analysis. Before there were computers, I think if you beam someone in from 1800 and you showed them the web today or the web 20 years ago, they would say, oh, it's closest conceptually to a library. But the problem is that this library has no archival feature. So it's as if you have this enormous building that's full of books, but sometimes the books go missing. And every 20 years, basically, the entire contents is forgotten and replaced. So this is like a problem that is in some sense recurring. So it's a larger problem of a problem, or a larger version of a problem that was already there and has always been there in the history of archiving. The history of archiving can essentially be summed up as we store the knowledge until eventually, unfortunately, something terrible happens to the location in which the knowledge is stored. So that can either be fire or flood. The Library of Alexandria fire is, of course, the one that everyone remembers. But it can also be, attacks by military kinds of militaries associated with groups of power. People find the control of information to be a valuable thing, and subsequently it's often under threat. And archives are eventually where that fight ends up happening often. And if you had to sum up why we thought that it was important to start addressing this problem now, you can put it into this simple maxim, I guess, by George Orwell from 1984. He said, "He who controls the past controls the future, he who controls the present controls the past." This idea that having control over what people understand of the past controls the way that those people interpret the present, and that changes how they act in the future. So by changing their perception of the past, you can affect how they act in the future. And this, I think you can see, history is littered with examples of where this has happened in practice, not just in fiction. So this is why we built the arweave. The web connects people over vast distances. The arweave tries to connect people over vast distances of time. We're essentially working on that other axis. And on top of the arweave, so there's this sort of base layer that we call the arweave, which is really just like a document store system. You put a piece of information into it, and it has sustainable economics to make it perpetuated essentially forever, and also, uses decentralization technology and peer-to-peer networking to put copies of the data in dozens and dozens of countries across the world. Actually, I'm sure it'll eventually be hundreds of, over 100 countries, 200 in total. Yes, and then on top of this base layer protocol, we have what we call the tunnel web, which is all of the information inside the arweave exposed in browsers. And this means that you can point a browser at an arweave gateway, stroke, and then a transaction ID, and you can be served back the data that is stored in the archive at that location. And that link, the gateway might change, but the link, the identifier, will never change. And this essentially creates a web where nothing is forgotten ever. So that's the idea of the current web. This is what we started work on, I guess it was about 3.5 years ago now, in total. And then 2.5 years ago, actually on the 69th anniversary of the publishing of 1984, we launched the network. And the first piece of information that was stored inside it was a copy, in fact, of 1984, the book, as a text file, which we downloaded from the Internet Archive, I believe, actually. Okay, so this is the principle of what the arweave is, but how does it actually work? Well, as I was mentioning before, blockchains allow decentralized replication of data globally. Arweave is just an expansion of this idea. And in fact, I guess at the time they were just my friends, but now close colleagues. We were very interested in blockchain technology from, I first encountered it back before Bitcoin passed parity with the dollar, so somewhere before Bitcoin was worth over $1, I think even 30 cents or something like that. And then by 2012, 2013, we were very interested in this, and we were mining Bitcoin, while also studying computer science and working on distributed systems. And then around the time of 2017, I was working on a decentralized operating system project as part of my PhD. And we had this sort of realization one day that while it looked like in the world around us, things were heading in a more and more volatile direction, like a direction in which those potential threats to archival integrity were growing. So the potential in the West, which had largely been, say, a freer place before, there was a growing potential, still unlikely, but a growing potential that the archives that people were creating would lose their integrity one way or another. And at the same time, there was a growth in blockchain technology and consensus mechanisms, particularly. People were starting to get creative with the way that blockchains distribute and compute on top of data. And we realized that you could actually take this base layer, this base idea of, okay, so when you give a transaction to the network, the transaction is what we call gossiped around the network to everyone else. So the user gives it to one person, and that person gives it to everyone else, or gives it to other people who give it to others, until you essentially cover the entire network. And then they write that data, they come to consensus, they come to agreement on what the change created by that transaction will be in the network, so how the state will change. And then they agree upon that, and they write it into what we call a block, which is essentially just a big chunk of these transactions, all processed at once. And then they move on to the next block, and they continually do this. And so you have a consensus mechanism about data that is being entered into a ledger that is, without a single centralized point of failure. There is no place like the physical Internet Archive where you could go and cause a problem for a network like Bitcoin. And so we realized that that is of what you would need in order to make a ledger of history that has very high integrity, cryptographically verifiable integrity. We can, with mathematics, prove that the ledger has not been altered over time. But of course, the problem is Bitcoin, the block size is essentially 1 megabyte. So you can only store a very small amount of data inside it. And at that time, it was actually growing, the cost of storing a piece of, just a financial transaction, which is just like, I think around 400 bytes into a block on the Bitcoin network. Just those 400 bytes were starting to cost you $30. So this is obviously not an appropriate kind of system to store very large amounts of information, potentially like newspaper articles or primary sources of history, maybe PDFs of, all sorts of things. And we'll get to what ended up being stored in the system later. So we realized that if we could just address the problem of how do we make it so that this ledger can store very large amounts of information, and then also the kind of corollary problem, which is like now you've got large amounts of information into this ledger, how do you set up the incentives appropriately such that people are pushed to store that information for long periods of time? And so we created a system that we call proof of access, which essentially enables you to provide simple enforcement of large-scale data replication. So the simple version of understanding how this works is, well, a Bitcoin block is attached to the last block. So it has a hash of the last block. You can think of it like a digital fingerprint, if you want, of the piece of data inside that block is nested inside the new block that we're creating. And so then you can cryptographically, using mathematics, go back and check the integrity of the chain of blocks all the way to the beginning, to the what we call genesis. So it has a single link. That's great. And then when you want to generate a new block, you have what we call a proof of work system. So you're essentially generating a race where all of the nodes in the network, all the computers in the network, are guessing random numbers to see if they've got all of these transactions, and then you guess a random number, and then we try and generate this fingerprint. Does this fingerprint, is it essentially below this other number? So is it one of a billion, trillion, quadrillion, in rarity? And the idea is to just push those machines to guess as many of those random numbers as possible until one of them guesses a number which has this property, which is very rare, and then that allows them to propose a block to the system, to the network, and they get to be rewarded in bitcoins for those blocks they're producing. So, and then everyone else validates that the fingerprint of the block with the random number and all of the contents of the transactions are all correct, and if they are, they add it to the end of the network, and that's essentially how Bitcoin works. With Arweave, we changed this so that it wasn't just a hash or a fingerprint of the last block that we were including in the next block. We also include the entire contents of a randomly chosen old block from the network in the production of the next block. In order to take part in that race where you might gain a reward, you are required to store those old blocks. And this enforces large-scale data replication in many places. So now there's hundreds of nodes in the Arweave system, maybe over 1,000 at this point. And they are incentivized to at least have access to that information. So they can store the information locally, but they can also rent access from someone else. But one way or another, if you want to take part in the mining of the system, you have to have access to that data. And this offsets some of the work or value expenditure that is involved in the Bitcoin block production process to valuable storage of information, and that information is essentially a library of useful knowledge. So that's broadly how the technical side of this works, at least relative to Bitcoin. But the economics are maybe more interesting. So Arweave transactions, instead of paying for a piece of storage for a length of time, what we would call contract-based storage, we instead do something very different, which is we add to a storage endowment. So in a typical relationship with like Alibaba or Amazon, if you give them a file to store, then they're going to charge you for a period of time or an amount to store that file for a determined period of time. And then it's going to stop. It's a contract. Well, with Arweave, what we do instead is we say, okay, when you put a piece of information into the network, you pay for the storage of that piece of information for 200 years up front. And that sounds like it costs a lot, but actually storage is so cheap that that's essentially ½ a cent per megabyte. Then we use the interest on that principal that we've already put up to pay for the storage of the information, the interest on the principal, rather than the principal itself. So you can kind of understand it conceptually like this. We need to just make sure that one invariant remains true at all times. We call it the storage sustainability invariant. So for every block in the system that is, or every block in the block weave, which is the kind of data structure that we've created, we need to make sure that the reward in total that a node receives is greater than or equal to the size of the network, so the amount of data that's being stored, multiplied by the price for storing a gigabyte per block period. So this term on the right-hand side, you can think of as really saying the price for storing the state of the network, all of the network right now. We need to make sure that the reward is higher than that at every single time step. And the way that you do this is by using the interest on a principal rather than paying people directly. So instead of taking interest in the typical financial sense, or in the dollar sense, we take interest in the form of storage purchasing power increase. So you can see here, this is a logarithmic scale decline of the cost of storage over the last 40 years. And what you see is that it's on a constant exponential decline. Approximately the rate of storage decline is on average 30.5% per year. And that means that at the year zero, when you put data into the network, you're paying 200 years worth of storage at current cost upfront. And then after the first year, instead of having less storage purchasing power, you've actually got more. You've got more than 260 years in a typical year. Or a typical 12-month period, you will end up afterwards having 260 years of storage purchasing power. And then after the second year, you end up with 338 and so on. So rather than the storage purchasing power of your principal declining over time, it's actually, while you use it to pay for storage, it's actually going to increase as long as the storage cost decline stays above 0.5% per year. And again, that's a safety margin of what, 61-fold. So it's very safe margins that we're using. And the other question you might have about that is like, okay, well, yes, over the last 50 years, the cost of storage has declined by 30.5% per year on average, but that doesn't mean it will continue doing so forever, right? And so we looked in depth into where we are in the storage decline curve. So what are the factors that go into this? The first factor is the data density of the storage medium, and then it's data reliability. So data density, we are at approximately 1 times 10 to the power 12 or 13 bits per cubic centimeter at this point. In research, we've already reached 1 times 10 to the power 25 bits per cubic centimeter. And the theoretical maximum data density that could ever be reached is approximately 1 times 10 to the power 68 bits per cubic centimeter. So we have a very long way to go. In fact, actually, if we were to continue at that 30.5% essentially increase in data density per year, it would take us 433 years from this point to reach the end of that cycle. And then on top of that, we're also looking at increases in data reliability, which essentially give us the same type of interest effect on the effectiveness of our storage. So you can see that this pattern will continue for a very long period of time. In fact, likely thousands of years in total. And when we say permanent modality, we mean essentially past the point at which any human life is likely to live, or any human-like life, because we also believe that AI, which probably in some form of cybernetic systems will probably replace us, and they will also have a very, very, very strong interest in data preservation, I am sure. So when we say permanent, we're pretty damn sure that this system will outlast humans and human-like forms with this pattern. Okay, so this is all the kind of theory. Why we chose to do this in the first place, how it works from a technical point of view, how it works from an economic point of view. And now we've been going for 2.5 years in practice. And as described, the goal of the system was to close the Orwellian memory hole, make it so that it's impossible for anyone, anywhere in the world, to make a piece of information disappear once someone else has published it. And we already found that this has been used in practice by reporters to essentially catch the Russian government, for example, essentially trying to manipulate and remove records of history. So this was an incident in which it was, I think, December 2018, in the Kerch Strait in the Ukraine-Russia border zone. A bunch of Russian ships essentially barged into some Ukrainian ships who were trying to pass through a closing, a strait, a narrow area of the ocean, and they took a whole bunch of Ukrainian soldiers, I think, or seamen, hostage. I think it was around 28 sailors. And then, what was very interesting was that one of the Russian propaganda outlets that publishes in English, it's called Sputnik, published an article in which they were very highly pro-Ukrainian, which was obviously a deviation from the expected propaganda line. And in fact, this article was only online for 14 minutes, I think, in total. But during that period, someone had archived it and added it to the... And then, after the fact, once the thing had been deleted, there are a whole bunch of warning systems in the network that flag to people when data is deleted. It was noticed, and then, essentially some large British newspapers started to write about it. Because it was a time in which, the Russian government was essentially found to be attempting to alter its own statements about geopolitically important events that were happening in the world. And of course, as soon as that user had pressed that button to submit that piece of information to the network, it was replicated in dozens of different countries, so across many, many jurisdictions. So many that it would not be feasible to coerce every person that had a copy of that data to delete it. And it was backed by sustainable, strong economics that were going to incentivize people to replicate that data, essentially indefinitely. And so now, of course, you can go back to that piece of information today, and find it just as it was beforehand, or at the beginning. And of course, what's really interesting is that because this system is based on that mechanism of work that I described previously, once it had been buried in the network, so once it had been sort of positioned under many further blocks, the computational cost of essentially trying to erase it or replace it or alter it in any way would have been extreme. And so at this point, we can look back at this piece of information and we can compare it to the hash that we have inside this network. And we can say with mathematical certainty that this piece of information has not been altered. So now it's 2 years down the line, but maybe 20 years or even 200 years from now, it's going to be extremely valuable to be able to say with a very high degree of confidence, an extraordinarily high degree of confidence, that this piece of information has not been altered during the time in which it has been archived. It's like a fundamentally new ability that no archive could really give you before. And it's not just Russia. There are also numerous press releases by the Italian government, for example, that are stored inside the Arweave network. The Italian government, I think after a change of prime minister, perhaps unsurprisingly, deleted from their website. They're no longer available from any official government sources. But of course, as you can see at the top of this screenshot, there's an arweave.net link there. So arweave.net is one of the gateways. You can replace that with any other gateway ID, gateway URL. And that ID afterwards, what we call the transaction ID, which starts QW, blah, 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 blah. This is one of those fingerprints that I was talking about. And that fingerprint can be used on any node in the network, any of hundreds of nodes spread across dozens of countries to access that same piece of information. This is like locked into history now. It's not going anywhere. And it's verifiable that that is the case. And there's numerous other examples of this in practice. Some that, we won't discuss today, but there are many, many examples of this. There is a website called BitSearch, which is essentially an Arweave permaweb search engine. BitSearch, spelled as you'd expect, but with .ch at the end, rather than another kind of domain name. Which allows you to basically search for any topic and see all of the content about that topic that's been written into the Arweave, and then see when it was written into the Arweave. And it's an archive and a library that just never forgets anything. And it's being filled with more and more information all the time. And we think that this is a more and more serious, pressing need. When we started the Arweave project, the situation in the West was such that we feared that there was a 1 in 10 future, maybe a 1 in 20 future, where access to information about the past would be, it's not something we could rely upon. And now, what, 2.5 years after the launch, 3.5 years since we got started, but we're finding that 1 in 20 is maybe one in many, many less. Like, the world has become much more unstable since that point. And governments are becoming increasingly extreme in the way that they are dealing with moderation of internet services, let's say. And it's not just governments, of course. The Internet Archives themselves, which, we're good friends with the Internet Archive, and we work with them to store millions of torrents of information that's stored inside the archive, so that we get that verifiable timestamping, so that if you give me a piece of information that you say was from the Internet Archive 100 years from now, I'm going to be able to check it against this timestamping that's inside the Arweave network. It's the same information. So it's not the information itself, but the metadata and that digital fingerprint is stored into the network in such a way that we can verify that that data is the same later, but not actually the whole content yet, because it's just a very large amount of information and no one's been willing to pay for it yet, but I'm sure someone eventually will. Yes, we work very closely with them, but recently they've moved down a path of, I would say, something along the lines of not neutrally portraying the information that is stored inside the archive. So they are providing so-called fact checks on the information that is stored inside the archive, which I think in practice leads to a situation where we are back to sole arbiters of the truth. Because, of course, who really gets to choose what is true? Who gets to check the facts? And indeed, who then checks the fact checkers? Typically, it's been the role of an archive to be a neutral store of information, which is retrieved later and presented without context or bias. Well, the Internet Archive has moved away from that. And I think that's a pretty dangerous game. And so, yeah, the need for a neutral archive. And I think the only way to truly achieve a neutral archive is mappization. Yeah, I think that need is rising. And so I'm very glad that we started on this path and that it progresses as it has. Anyway, yes, thank you very much for your time and your attention. Yeah, I'm looking forward to the rest of the conference.
Thank you so much, man. Thanks so much for sharing today. So can you just stay a little bit longer? Then we'll have a QA session later, after the next one.
Absolutely.
Thank you so much for that. All right.